Today we are going to talk about internal resistance of a cell. An electrolytic cell, as you already know, is one in which you have an electrolyte and an electrodes, and the chemical reaction produces a potential difference between them. This potential difference is called the EMF of that cell. We have a Leclanché cell here, and when we check its potential difference between the two electrodes, when it is not connected to anything else from outside, that means no current as such is being drawn from it. 1.4 is the value for the potential difference that the chemicals are producing over here, and this is our EMF. What happens when we place this in a circuit? That means draw some current from it. In order to check that out, I have a resistance box here which has small resistances, and the highest value is about 50. 50 ohms is quite a lot. So, we will not use so much, and if we connect this now across our cell and use our voltmeter to check out the potential difference that is between the two terminals, do you think current will flow? Yes. Why? Because now there is an external path for the current to flow, and say I take out 5 ohms here. So, 5 ohms is the resistance in the circuit. The current flows from the positive through this 5 ohm that I have selected and back to the negative terminal. Do you think current flows through the cell? Well, it does, from the negative to the positive, as we had seen the chemical action taking place, making the negative terminal and the positive terminal. So, it is the flow of current in the outer circuit is from positive to negative, and inside the cell it is from negative to positive. This is the conventional way of looking at how the current flows, because at the time when the current flow was decided in circuits like this, it was not known that it was electrons that were responsible for the current in a conductor, and that picture has continued to say that the current starts from the positive terminal, goes through the resistor and to the negative terminal. Let us check out what is the potential difference across this here. I wonder if you are expecting anything different to have happened. Let us check it out. The positive of the voltmeter goes to my positive terminal, and the negative of the voltmeter I am attaching here to this zinc rod. Notice how low this potential difference is. Initially, when this was not connected, the potential difference was 1.4 volts. Now that current is drawn in this external circuit, the potential difference across the two terminals has dropped. The reason for that is that there is internal resistance of the cell offered by the electrolyte, which is responsible for taking away some of that potential difference. So, the potential difference across this resistor, which is external, and the potential difference across the internal resistance of this cell should add up to 1.4 volts. So, let us take a measurement here. This value is 0.15 volt. Can we calculate this value of internal resistance? We could if we knew the current in the circuit. I do not have a ammeter right now, I have only a voltmeter. Well, I am going to use Ohm's law and find out how much current is flowing in the circuit by finding out the potential difference across these two terminals. Let us attach it here, and I have 5 ohms there, and the potential difference here is 0.15 volt. So, the current would be V upon R, which will be 0.15 divided by 5. This value of current will be 0.03 amperes. I can take that value and now calculate what will be the value of potential difference which is coming out here. In order to do that, the potential difference that we got here between these two, also called the terminal potential difference, V is equal to E minus I R. What is I? The current flowing in the circuit, which we have just calculated. So, then we can write down E value to be equal to I R, which is this resistance, plus the current multiplied by internal resistance of this cell. So, in effect, the total resistance would be the resistance outside and the resistance inside. So, if capital R is to show the resistance outside and small r to show the internal resistance, that multiplied by the current should give me my value of EMF. That indeed is an easy way of calculating internal resistance. We are going to now do some problems. We are going to see how we can calculate the internal resistance in each of those cases. Supposing the potential difference across the terminals of a cell is 3 volts. That means it is the EMF, because it says when it is not connected to a circuit and no current is flowing. So, 3 volts is the EMF given. When the cell is connected to a circuit and a current of 0.37 amperes is flowing, the terminal potential difference falls to 2.8 volts. What is the internal resistance of the cell? Let us look at our equation. E is equal to V, the terminal potential difference, plus the current in the circuit into the internal resistance. So, E minus V is equal to I R, or we can say E minus V upon I is equal to R, the internal resistance, which from the values that are given to us will be 3 minus 2.8 divided by 0.37, and if we calculate that, it comes out to be 0.54 ohms. So, 0.54 ohms is the internal resistance for which these specifications were given. Of course, the internal resistance for all cells is not the same. It depends upon the electrolyte, the distance between the electrodes, the temperature, dilution and other factors. Let us take another question. If we plot a graph of terminal potential difference V against circuit current I, we get a straight line with a negative slope. This negative slope, we have to explain why negative. So, let us take a look at this explanation. The intercept on y axis is equal to the EMF of the cell. The gradient of the graph is equal to minus r, and how do we get this to this conclusion? E is equal to V plus I R. E minus I R is equal to V, and V is equal to minus I R plus E. So, when we are making a graph of terminal potential difference and the current, our equation matches y is equal to m x plus c, and from here we can see that minus r is the slope of this line, it is negative, and E is the intercept. So, from the graph we see that the intercept on the y axis is my EMF, and the gradient or the slope, which is minus r, is going to give me the value of internal resistance of the cell. We can take another problem. Supposing we are given a graph with values such as this one and asked to find the value of EMF of the cell, the current when the terminal voltage is 0.8 and the internal resistance of the cell. What will we do? We will extrapolate this line and see where it touches the y axis. In this case, it is 1.4. So, the potential difference of 1.4 would be the EMF of the cell. The slope of this line will give me the internal resistance, and the other question as to how much current is being drawn if the terminal voltage is 0.8, that can be read off straight from here. So, graphing it out and working with simple problems can help us calculate the value of internal resistance. though not a big value, but it can change the way the cell works and operates. Most of the cells in the market do have some internal resistance. These values you can check out by doing the experiment as we have done just now.